So I'm going to tell you about a shapeable material without plastic deformations. And this is work I did with Tom Whitten at the University of Chicago. And I wanted to start with an apology or a warning that I'm not a mathematician. So some of the stuff I say might be trivial to you, and I'm probably going to use different words that you're the ones you're used to. Okay. I'm going to talk about an elastic sheet, but I want to start with talking about paper. And I want to start with doing an experiment that I encourage you to do yourself. If you have a piece of paper, it will help you visualize the talk. So I have a piece of paper. Take it in your hands and put pressure on it from both sides. It will buckle up. But when you let go of the force, it's going to go back to being completely flat. Now, repeat the experiment, but first crumple this piece of paper into a little ball. Then flatten it. And now put pressure on it from both sides. It will form, again, a buckle. But now when you let go of the force, the shape remains, right? So this is one stable configuration of paper, but I could have done it. There are many others. So this is another one, and I can create a little flower and put it in my hair. And all of these are going to be somewhat stable. And this is what I'm going to mean when I say that a material is shapy. So let me define it better. When I say that something is shapy, I mean that when you put a force on it, you create structural change, but that doesn't require any further destructive change to it. That's the first part. The second part is that I want it to be somewhat stable to further perturbation. What do I mean by that? I mean that I have my little mountain, and I can put a small amount of extra force on it, and it's going to go back to this configuration. I need to apply more force for it to go to a new configuration. Okay? So this is paper, and paper is shapy because it's plastic, right? When I crumpled it, I formed all those ridges and vertices that I cannot undo, or that it will take me a lot of energy to undo and go back to a completely flat sheet. But I'm not going to talk about paper. I'm going to talk about an elastic sheet. And the question is, what's the problem with paper? First, plasticity wears out. So if I were to take this mountain and leave it here and come back a month later, it's going to flatten out a bit. And second, plasticity is complicated. And the question that Tom, my postdoc advisor, asked is, can we have something which acts like crumpled paper in that it is shapy, but that doesn't have plasticity, so it's going to be completely elastic. And therefore, it's going to be easier to control and to understand. And maybe if we understand what causes shapeability in an elastic sheet, we can understand paper better too. Okay. So, so I'm going to talk about an elastic sheet, so the generalization of paper to a non-dissipative material. I'm going to keep my paper, I'm going to need it. It's going to be cleaner and easier to understand and control. And I'm going to tell you about two ways in which we did this. And when I say we did it, it's only in the computer. So all tell you about today is computer experiments. We don't have a real-life realization of this. We tried to 3D print various versions, but all of them were too fragile and broke. But maybe one day I will have an actual one to show. I'll tell you about two ways in which we did this. One is the random lattice. The second, which is an ordered array, we call the puckered lattice. There are many other possible ways to do this. Those are just two examples. And questions that we will address is what are the conditions that are needed for a material to be shapy? How shapeable is it? How robust is the shape that we created? And a bit about where do we think the memory of the shape comes from. OK, so elastic sheet. What do I mean by an elastic sheet? All of the talk will be on those triangular lattices of springs. But they're not going to be, so this is a regular lattice of equilateral triangles. Our distances between the springs are going to be different. They're not going to all be the same. But the idea is the same. We have two nodes, or many nodes in the lattice. Between each two nodes, there's a spring. The rest length of this spring is going to be Li. And all we do is rewrite the energy of the function, which is just the energy of harmonic springs, and minimize it. And look at what the minimal energy configurations look like. OK, so if we look at, for example, at this cartoon of just a regular triangular lattice, this is not going to be shapeable. It's going to have just one minimal configuration. You can try to shape it, but when you relax the energy, it's going to go back to being flat. So what can you do in order to have shapeability? The first way we did it is to have a random lattice. What do I mean by a random lattice? What we do is we take this triangular lattice, and then we add a bit of randomness to the rest length of the springs. And just between 5 and 10% is enough. This means that if this was my triangle before, once I add a bit of randomness to it, it's going to look more like the left-hand side shape when you relax the energy. And if you try to do it the same thing with this hexagon of equilateral triangles, once you add randomness to them, the energy is going to be, the shape is going to be frustrated when it's flat. Energy is going to be high. And in order to relax the energy, what happens is that they will pop out of the plane, right, and create a pyramid-like structure. And once you do that, you can have two possibilities of pyramids. One of them is going to face down, and one is facing up. So the middle node here is now bistable. And since in my random lattice I'm going to have many such nodes that are bistable, the entire sheet is now metastable. And this is a bit, and once you relax the energy, you get shapes like this, which looks a lot like crumpled paper. And crumpled paper has many bistable points as well, right? So I can look at one of those nodes. It's a mountain, and I can press it down and turn it into a valley. Yes, so many bistable points result in metastability of the entire sheet. That's the first system. And the second system is the puckered lattice. And for that, we realized that actually you don't need randomness to have metastability. This paper is random, but you can have metastability in an ordered array. And think of an ordered array of just pyramids, hexagonal pyramids. each of these pyramids is bistable. It can be pointing up or pointing down. So the entire sheet is metastable. But that's not enough to have shapeability of the entire sheet. Why not? Because, I mean, each one can be pointing up or pointing down, but you need a correspondence between them in order to create global curvature. What do you do in order to have correspondence between them? You need to somehow break the symmetry of the pyramids. To do that, our scheme is to have 3 different lengths, rest lengths of spring, not just 2, which means the black points, the black springs, which are the hexagons, are the shortest distance, and in the middle we're going to have longer springs, but the longer springs are going to be interchangeably intermediate, which is the green, and longest, which is the red. And now when you relax this hexagonal sheet, it's the basis hexagon is not going to remain flat. It's going to be a bit out of the plane. And this is enough in order to have a correspondence between neighboring hexagons. And now when one is pointing up, the other one is going to it's going to be a bit preferable for it to be either pointing up or down. You can see, so here in blue is a completely symmetric hexagonal pyramid, and purple is what we're using. So it's just. What is the what?
Is there a systematic means
for
coloring, or is the coloring random?
No, so it's yellow, green, red, and then the next one is going to be 60 degrees off. It's going to be, I think, perhaps, no, this picture is the same. But yeah, so red, green, green, and the next neighbor is an exact replica of it. Just interchange. I think the version that we found was more shapy is when we actually turned the next neighbor is going to be twisted by 60 degrees.
Okay, just trying to deduce the color.
Yeah. So this shape is still going to be symmetric, but not completely symmetric like if you have just 2 lengths. And when you relax the energy of those sheets, you get shapes like this, which are, you can see, much more regular than the random lattice that I've shown you before.
So all in all, you have only 3 different lengths.
What?
All in all, you have just 3 numbers
Yes.
controlling the entire structure.
Yes, just 3 numbers. You have a basis of hexagons, which are the shortest, and in the middle of the hexagons, you have longer ones. Okay. So those are the sheets we used, but when we tried to shape them, we realized that they weren't stable to an outer perturbation. So one needs to ask, when is the system stable? And this has been talked about earlier today, and in other days as well, yesterday. So I'll go over it briefly. A system is stable. So Maxwell has the constraint counting argument, meaning that all you need to do is count the number of degrees of freedom you have in the system and compare it to the number of constraints. In our case, we have n nodes. Each node has 3 degrees of freedom, so 3n degrees of freedom minus 6 for rigid body rotations and translations. And then compared it to the number of constraints, how many constraints we have, it's just the number of springs. So if I'm looking at one node, it has 6 springs. That's divided by 2 for double counting, meaning 3 constraints for each node. So free constraints, 3 degrees of freedom, sounds just about right for it to be stable, but the problem is we're talking about finite systems, meaning that at the edges we have missing springs. And the number of missing springs is going to be proportional to the perimeter of our lattice. I plotted some of them here in red. To be more specific, we have 4L minus 1 missing springs. And when you have missing springs, then the system is not completely rigid, and you have floppy modes. Those are modes, that transformations of the nodes that cost you no energy. And we can characterize them a bit better. If you want to know what do those floppy modes look like, what you need to do is find the dynamical matrix of the system, which is just the second derivative of the energy taken at the minimal value, and find what are the eigenvalues. The number of zero-valued eigenvalues is the number of floppy modes you have. And the eigenfunctions corresponding to them are what those floppy modes will look like. Another way to put it is that you want to find the null space of this matrix, and the null space vectors are the eigenfunctions. Or it's the question to the answer, if I have this energy landscape, very simple energy landscape, I take the minimum, but there may still be directions in which I can go along with without paying any additional energy. Okay, so if we do that, we find that for our the usual lattice we're using, which is a 7 by 7 lattice, we have 27 floppy modes, or 27 eigenvalues of 0 value. And in order to visualize them, what we do is we sum over the null space vector components square on each node. This tells you like the amount of floppiness that this node has in the x, y, and z directions. And on the left here, the city is what the floppiness looks like for our sheet. You can see that most of the floppiness lives in the perimeter, and that most of it is in the z direction. On the right-hand side, this is just the norm. It's another way of visualizing the same thing. It's just the magnitude of floppiness on each node. Black means a lot of floppiness. White means almost no floppiness. So the middle part is mostly stable, and floppiness, again, sits at the sides, which is what we would expect, since at the edges we have missing springs. So you may ask, well, what do we care about this floppiness? If it's mostly at the sides, the middle should still be shapeable, which is true, but so why don't we just take bigger and bigger lattices, and then we don't care about the edge? The problem is that when you do that, you find out that when you take bigger and bigger systems, you have many more eigenvalues that are not completely 0, but are close to 0. And then your system is also not stable. These correspond to bending modes of very low energy. So we would want to stick to small systems that have many metastable points, but not a lot of, but can still be rigid. In order to do that, we want to get rid of this floppiness. So how do you get rid of floppiness? A bad idea would be to fix the edges of the edge nodes, because then you sort of threw the baby with the bathwater. You get rid of floppiness, but the edges are fixed, so you can't really shape it. So we thought of two other possibilities. There are other possible ways to do that. This is just what we did. One is to add extra springs at the edges. Those are the red ones here. So these are just next to nearest springs. The second way, which is more physical in a way, is to add bending energy. So this is energy penalizing deviation from flatness. Just a tiny bit of bending energy. And the idea is, in both cases, the idea is to add more constraints so that your system is isostatic or more. It's enough, it has enough constraints for it to not be floppy.
Excuse me, so about the second one, it seems like you have no flat region at all in your pyramid model.
That's true,
So
I don't.
how would you
So the energy is not going to be zero. Even the minimal energy is not in this case. But it's just a tiny, really small amount compared to the energy of the springs. Once you do that, it works. You can shape your elastic sheet, and the shape is going to be stable. And these are a few examples. So what I do is, first I take all the springs and I put them in a desired configuration. For example, half a cylinder. The energy of the springs is going to be very high, but then I let it relax. And what you find out is that it doesn't deviate much from the initial configuration. So in this column is random lattice with bending energy. This one is random lattice with stiff edges, meaning extra springs at the edges. And this is just an average along the x direction to see that all of the shapes pretty much sit one on top, are not too far from one another.
So, excuse me, so when you say random edges, you really do it at random, so you just run some. I mean, when you say random, it's truly random, so you just flip a coin, which edge to add.
Yes, which length, yeah,
So,
which rest length to choose from.
okay.
So you can do shape it as half a cylinder. You can shape it in this wavy form, but too much curvature, so strongly curved shape didn't maintain the curvature so well. You can see a circle didn't hold that well. So there's a limit to how much curvature you can impose on the system. The previous slide was for a random lattice. I wanted to show you that the Puckered ordered array also works. So on the left, I tried to shape it in this cylindrical shape, and it retained its shape and was stable to perturbations. And I wanted to show on the right that when I tried to do the same thing, but I didn't have 3 different spring lengths. So here I had just 2 lengths. This is just regular pyramid symmetric ones. Once I relaxed the energy, it went back to being flat. And of course, same thing if all of the lengths were the same. Hysteresis. So our system has memory, and a way to show and study memories is to check if it has hysteresis. This means that the current shape is going to depend on the history of what I did to my sheet. And in order to study hysteresis, what we did was to take the sheet, fix 3 of the nodes. So one is going to be fixed completely, one is going to be able to go along a line, and one is free to go on a plane. This is just to kill the translations and rotations, degrees of freedom. And then we took the middle spring, a middle node, and force it a bit up. Once you do that, the sheet is going to obtain some curvature. And then you let go of the middle point, you let it relax, it will go down a bit, but there's going to be some average height, which we measure. Then you repeat it again. So you take it the middle node a bit more up, and relax it, and so forth, and then you go down. And this is what I plot here. So the y-axis is the average height once the sheet is relaxed, and the x-axis is the height of the middle forced point. If there was no hysteresis, if there was no memory in the system, going up and going down would follow the same curve. But in this case, since there is memory, I'm going up along one curve, and I'm going down along a different curve. Yeah, which means that the shape remembers the previous location of previous configuration. And so this is what I got when I actually didn't have enough springs, when my system had some floppiness. This is before I realized that I need more constraints for the system. And why I showed it in order to contrast it to what I got when I did add extra springs. So this is when the system is hyperstatic, when there are stiff edges, so more springs at the edges. And you can see that there's still hysteresis. So there's a loop here. There's also a loop here. Goes up along one way and down along another. But in the first case, each time I force the middle spring, the middle node up, it obtained a new configuration. And in the bottom case, you can see that it's different because here I have plateaus and jumps, plateaus and jumps. So not every time you force the system up, it will attain a new configuration. And this is exactly what we wanted. It's another way of showing that this system has some rigidity or some effective bending curvature in a way. You force it, it will not always go to a new shape. This is another way of seeing this. So here I sorry. So here I force the sheet in a cylindrical fashion, and then I got the sheet to sit on the red dots. Then I apply more pressure in a radial fashion, so more pressure causing it to obtain the shape in white. And once I relax the forcing, it goes to sit exactly at the position of the red dots, which is just a visualization of what I said before. Okay, so now what determines the shape? To begin with, the shape, an important ingredient is those bistable nodes. Right, we said that I have those pyramids facing up or facing down. And for the regular puckered lattice, we know exactly where are the bistable points because we constructed it in a pre-designed manner. But where are those bistable points in the random lattice? So I'll show you is that there's a correspondence between bistability and positive angular deficit. What's positive angular deficit? If you look at this hexagon and count the angles around the middle node, you'll get 360. If you do the same thing for this pyramid here, you'll get less than 360. So less than 360 is a positive angular deficit. Negative angular deficit corresponds to a saddle point. So really, it's the discrete version of Gaussian curvature. So we wanted to check if the bistable points, so this is, yeah, if the bistable points correspond to positive angular deficit. This is one example of one such experiment. A vertical red line means that there's that the node is bistable. A horizontal one means that there's positive angular deficit. And you can see that there are many pluses. But there are also cases in which I have positive angular deficit, but it's not bistable. And vice versa. This is, yeah, and I forgot to write the labels of the axis. This is a histogram of many such experiments we did. So I have many random lattices, check where are the bistable points, count the angular deficit and compare. The x-axis is the angular deficit, and the y-axis is just number of, it's just counting. And blue means that the node is positive, has positive angular deficit and bistable, which is in most cases. But you can see that when I have, when the angular deficit is small, then then you have many points which are not bistable anymore. So that is to say that bistability, so angular deficit is, there's a correspondence between that and bistability, but it depends on the magnitude of the angular deficit, and it depends also on the position of the neighbors. Okay, so bistability. Once we know a point is bistable, we want to see that it indeed dictates a global shape. So this is one such experiment. I have in gray, this is a regular Puckered lattice with all of the hexagons, the pyramids facing down. And then I take one point which I know is bistable, namely I think this one here, and I pucker it up. So I flip it up. And I get the shape, the black shape. And on the right, it's the same thing, but with mismatch between springs to be just a bit more. You can see that the resulting shapes have curvature, global curvature of the sheet. So another way of showing that bistability is important is these following experiments. So I take my, again, Puckered lattice with all of the pyramids facing down, and I force it to have a positive mean curvature. So like that. This is the forced shape. Once I relax it, it maintains the shape. But if you try to do the same experiment going the other way, then forcing it the other way, then once you relax the sheet, it will not maintain the curvature. It will go back to being completely flat. What does this mean? It means that the global curvature is in somewhat dictated by the local curvature of the pyramids. You can't go really against what they prescribe. So at first we thought that those bistable points are all we need to care about, those local bistable points, but we found out, but it's not the case. There is some missing ingredient which we don't know what it is, but it's not those local bistable points. And a simple way to see this is that I have two stable configurations when all of the bistable points are facing in the same direction. So I can have my sheet curved like this and all of the pyramids facing up, and it will be just as stable when it's completely flat and all of the bistable points are forcing up. So our dream was initially that I can 3D print this thing and I can tell you, well, press here, push there, and you have a chair. And if you're tired of the chair, you can press there, and you have a table. But it's not, it's not only those local bistable points that dictate the shape. So there's some component which is non-local. And to see that, you can repeat the experiment that we already did before. So you can have your sheet cylindrically shaped like this, and you can add pressure to it. And before I added a small amount of pressure, I let go of the pressure and it went back to the exact same shape. But now I'm going to add a bit more pressure so that it doesn't go to the same configuration. I'm going to add the pressure it takes to go to a new configuration. And I want to check what happens to what changes occur when I do that. So this is the fourth cylinder. This is when I added just enough forcing to drive it to a new configuration. And this is what happens to the nodes and to the angles when I did it. So the size of the dots, the red dots, mean how much they changed from going from left to right. And the width of the lines is how much the angle changed. So first thing is that the largest amount of change occurred in this node, which is not even a bistable node. It was a saddle point. And you can see that the change is also not local. So it's not here only in this node. And the angles change throughout along this line. And a good measure for how non-local is a change is to measure something which is called the inverse participation ratio, IPR. What it means is you're going to define some property psi, in this case either the position of the nodes or the angles, and you normalize it such that the sum over psi I squared is just 1, and then IPR is 1 over the sum of psi I to the 4th power. This is a good measure for non-locality because it's going to give you 1 if the change was localized in just one node, and it's going to give you n, the number of nodes, if the change is spread out equally throughout the lattice. And what we get in this case, in this experiment, was 12 when we measured the angles. For a 7 by 7 lattice, there are around 100 angles, meaning that 12% of the springs took part in this transitional, configurational change. Yeah. So that's all I wanted to say. We've seen two forms of an elastic sheet that can, we've seen that an elastic sheet can be shapeable. We've seen two ways in which this can be done. One is random, one is more ordered. We saw that bistability is important, but global curvature is not just the sum of those local bistable points. So there's another ingredient which is non-local. We still don't know what it is. We would like to find out more about it in order to understand better how does this shapeability come to be. Yeah, that's it. Right.
And in fact, that people in shape memory materials have sometimes built paper models illustrating some of your things. And so I just wanted to mention that there's that, and there's connection between that and also topology optimization and the theory of composite materials. And,
I don't know what that is. I know the first one. I don't know the second.
Shape memory materials, it's sort of interesting that there's a lot of advances recently understanding hysteresis, and so in particular they're now getting materials that can go through a million transformations without fatigue, and having very small hysteresis actually. Yeah. Anyway, there's probably a lot of cross-pollination.
Yeah. Yeah.
But this is really interesting.
What was the name of the second material? Sorry. Shape memory materials again?
The connection between shape memory materials and topology optimization, which is a problem of trying to find, maybe you're given two materials and you want to find some sort of layout of those two materials that optimizes properties. And it sort of makes sense that even though you start with two materials, the optimal configuration uses composite materials. In other words, you can have microstructure, and the problem there, choosing the best microstructures, is intimately tied with questions of quasi-convexification and shape memory materials.
I have a quick question about the pattern on your paper. Is there any correlation with vertices of higher degree having more meta?
So if you have more than 6,
Yes.
we
I mean,
didn't.
Are you doing any correlation between the degree of a vertex and some of these properties?
No, we didn't check at all. So we stuck to 6, which was like the limit of rigidity, on the verge of the limit of rigidity.
Any other questions? If not, let's end this. Oh, you have a question. Yes.
So when you are on the random lattice model, I don't know if you have explored the random variables that can be defined there, just to see, like, you talk about how big they could be that you can manage the structures.
Right.
So that would be a random variable. You can define
The size.
the size and other things, like how many are up and down or the saddle. But I don't know.
What's the, so the question is how many random?
No, if you have explored the behavior of the random variable.
Oh, yes. So we explored a bit the size, and the optimal size seems to be 7 for our system, which is why we chose to work with that. But so I think there's a way to still have shapeability even if you have larger and larger systems, but you need to have, it depends on the height of the system. So the ratio between the average height and the size of the system matters. If you want larger systems, you need a bigger height to obtain the same curvature of the global shape. And you can do that by prescribing like random height, for example, or height that dispersed throughout the lattice. And up and down, I don't know.